So here, suppose we have a second order homogeneous solution, and then with the assumption x of t to be exponential to st. Okay, so and here we already get the characteristic equation as a quadratic equation. So actually in high school you should have learned how to solve this quadratic equation. So the equation is nothing but s equals negative b plus or minus square root of a b squared minus 4ac all over 2a. Okay, so of course in high school you also know that the b squared minus 4ac is so-called the delta, and then we'll see whether the delta is larger than 0, equal to 0, or less than 0. Yeah, so we will also have these three cases here. So the first case is the simplest one. So we have a b squared minus 4ac to be larger than 0. So which means that we have distinct real roots, because this is a positive number, so we can take the square root. We have a positive number. So this minus b plus or minus this positive number, so we have two distinct real roots. Okay, so suppose these two distinct real roots is s1 and s2, which means that exponential to s1t is a solution. Also, exponential to s2t is another solution, right? Because here we try to plug in this function into here, and then we get this one to see what should be the s. And now we know what is s1 and s2, which means that exponential to s1t and exponential to s2t should satisfy this homogeneous equation. Okay, so and if you still remember, it is linear, which means that if we just multiply this function by a constant, just say c1 by c1, so this one should still be the solution to this equation. And likewise, we can just multiply c2 to this one, exponential to s2t. This one are all equation of this homogeneous equation. And suppose this one and this one are independent, because s1 and s2 are different. So now we can just add them together, so that the homogeneous solution becomes this form. Okay, so this is the first case. The point here is that okay, we have the homogeneous solution if delta is larger than 0. We solve these two roots, and the homogeneous solution is nothing but we plug in s1 and s2 here. So we have a c1 exponential to s1t plus c2 exponential to s2t. So this is pretty much it for the first case. And for the second case, if b squared minus 4az is 0, b squared minus 4az is 0, which means that this term is 0. This term is 0, which means that we have this we have complete roots. We have complete real roots. So which is nothing but minus b over 2a. So s1 equals s2. s1 equals s2. So now we cannot write the solution to be c1 exponential to s1t plus c2 to the exponential to s2t anymore, because s1 and s2 are the same. So this one and this one are actually the same, so which is something like a c times exponential to s1t. Okay, so but actually this one is not enough. We should have two independent solutions to this. So in order to the conclusion is that we try to multiply a t here, which is like of course you can just consider it to be c1 plus c2 like this, but c1 plus c2 are arbitrary constants, so if you just add them together, it's just still one arbitrary constant. But here we try to multiply a t here to make things not independent, to make these two terms are not dependent. Okay, so maybe you ask why we need to multiply a t. Yeah, actually you can just consider consider to we have an example later. So just try to remember these tiny step here. So we need to make it a first order polynomial rather than a single constant. Okay, so this is the second case, and then for the third case, which is the most complicated one, but actually the most useful one. So the last case is the delta is less than 0. This implies that we will have complex conjugate roots because this term is negative, so we take the square root, which is like square root of -1. Okay, so it will be complex conjugate roots. So alpha plus or minus I beta. I is square root of -1. But sometimes I will just write J rather than I, because for ECE or our textbooks use J's rather than I to stand for the square root of -1, because I is usually stand for the current. So for our textbook, I usually see J, so we seldom use I to stand for this one. So sometimes I would still remember to write I, but sometimes I just use J's. But so just take this in mind. I and J are all square root of -1. Okay, so this stuff looks a bit different. It just come out some trigonometry functions, cosine of beta t, sine of beta t. You might not know why, but yeah, one way is to just memorize it. And I'll try to explain it why it will be like that. Okay, so here you can see the complex conjugate root are alpha plus or minus I beta. So this is the real part, alpha is the real part. So we have exponential to alpha t in the front. And then for beta, we have cosine of beta t and then sine of beta t. And then we multiply these two trigonometry functions by a constant and add them together. So pretty much like this case, but here we have exponential and also cosine and sine here. So of course you can remember it, memorize it, and here I try to explain why it look like this. Okay, so now we know S1 and S2 is alpha plus or minus J beta. Okay, this is the complex real roots, and then we know x of t to be exponential to st, which means that if I just follow the logic here, we should write xc of t to be exponential to alpha plus j beta, and then all multiplied by t, and then c1 plus c2 exponential to alpha minus j beta t, something like this. If I just follow the logic here, I just plug in S1 and S2. Okay, and here S1 is alpha plus j beta, S2 is alpha minus j beta, so nothing special here. Okay, so here for exponential function with a plus sign, so we can just regard it as exponential to exponential alpha t, exponential to j beta t, and then plus c2 exponential to alpha t, exponential to negative j beta t. Okay, so here we can see the common factor exponential to alpha t, so we can just factor it out. So exponential to alpha t, c1 exponential to j beta t, plus c2 exponential to negative j beta t, like this. Okay, so at least we got this term. We got this term here. And then the next one is, this is a complex exponential function. The complex exponential function. And actually, it is a well-known equation called the Euler's equation. Euler's equation. Euler's formula. That should be Euler's formula, because we also have Euler's equations to stand for a few other equations. Okay, so this is the Euler's formula. So the Euler's formula is like exponential to j theta. Yeah, it should be cosine of theta plus j sine of theta. Okay, so you can just keep this in mind. So this is a very well-known formula called the Euler's formula. And if you want to know why it will be like that, it is related to the Taylor series in the calculus. I suppose you should have learned the calculus, Taylor series. So for the Taylor series of the exponential function, exponential to x, so this is just briefly proved, not so rigorously, but yeah, for mathematics major, they may not consider it to be correct. They also need to consider the convergency, but yeah, this is just a simple idea for engineering students. So for exponential to x, the Taylor series is nothing but 1 plus x over 1 factorial plus x squared over 2 factorial plus blah 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 plus x to the nth power over n factorial plus up to the infinity term. So if you have learned the Taylor series, you should know this. And for cosine of theta, cosine of cosine of theta, let me see, let me write cosine of theta, or maybe cosine of x, cosine of theta, let me see, cosine of theta will be 1 minus x squared over 2 factorial plus x to the 4th power over 4 factorial minus x to the 6th power over 6 factorial up to the infinity. And then for sine of theta, it will be x minus x cubed to over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th power over 7 factorial plus dot 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 up to the infinity. Okay, so these are the three Taylor series expansion for the exponential function, cosine and sine function. So if you just plug in x to be j of j theta, then it will just come out, some of the term will be complex. But here you can see j square will be -1, so it matches this one, and then j to the 4th power will be +1. So you can see all the real term is actually the same as the cosine of theta. And for the complex term, it's actually the same. For the imaginary term, it is actually the same as the sine of theta. So yeah, this is a proof for the engineering student for the Euler's formula. So you can just remember this one: exponential to j theta equals cosine theta plus j sine theta. Okay, so here we can make use of this Euler's formula here. So we can have exponential to alpha t times c1, and then here we have a cosine of beta t plus j sine of beta t, and then plus c2 times cosine of negative beta t. Cosine is an even function, so cosine beta t minus j sine of beta t. Originally should be plus j sine of negative beta t, but sine is an odd function, so the negative sign just come out, so we have something like this. Okay, so we can just gather this term, and then gather this term. So it becomes exponential to alpha t, and then c1 plus c2 cosine of beta t, for the first term, and then for the second term we have a j C1 minus C2 and then sine of beta t. And actually, for the original differential equation is a real equation, so we would expect this one and this one are real coefficient, which makes it like C1 equals the complex conjugate of C2. And in that case, if we just add them together, it will be a real number. And if we just subtract them, it will just a purely imaginary number. And multiply by j, it becomes a real number. So we can just rewrite this one to be Z1 and this one to be C2, so that it can be written as exponential to alpha t, and then C1 times cosine of beta t plus C2 times sine of beta t. If you don't like this way, you can just use A1, A2 here. So we just come up to here, A1 plus A2, and then A1 minus A2, and then we can rewrite all these things as a C1, C2, so that it turns out to be like this. So this is the third case for the solution, for the homogeneous solution. But actually, this one is the most useful one. Okay, so far any questions? Okay, so here we have some example. So let's see, for the first one, 2 times x double prime minus 5x prime minus 3x equals 0. So this is already a homogeneous solution. So we can write the characteristic equation. X prime to be x squared, x prime to be s, x to be 1. So we have this characteristic equation. And then we can just factorize or use the formula. So you can see S1 to be negative 1/2, and then S2 to be positive 3. So they are distinct real roots. So we can see the homogeneous solution to be C1 times exponential to negative half of t. So we can see we can write it as a negative t over 2. And then for the second term, plus C2 exponential to 3t. So we have a S1, S2 to be here and here, multiplied by t. Okay, so this is the first case, distinct real roots. For the second case, if we have a x double prime minus 10x prime plus 25x, so we can write the characteristic equation or the auxiliary equation like this: s squared minus 10s plus 25 to be 0. Okay, so this one is nothing but S1 and S2 to be 5. So according to the previous case, we can just take x of t to be C1 plus C2t exponential to 5t. Okay, so let me try whether we can show why this C2 will come out. So let me consider. So at least we should believe C1 exponential to 5t should be a solution. Because according to here, we know C1 times exponential to S1t is a solution. But why it comes out a t? So let us assume x of t to be let's say g of t times exponential to 5t. So we just skip the c1. C1 can be regarded as a part of the xt, part of the g of t. Okay, so let us plug this one into here, so we can see. Maybe I just open another page. X double prime minus 10x prime plus 25x equals 0, and then we already know xc to be xc1 to be c1 exponential to 5t. Okay, so here we assume xt to be exponential to 5t times g of t. Okay, Okay, so let's us just plug this one here. So for the second derivative, the second derivative of this one will be 25 exponential to 5t times g of t, and then the first derivative will be 5 times 2 is 10, and then exponential to 5t g prime of t, and then plus exponential to 5t g double prime of t. So this is the second derivative of x of t, and then minus 10, and then here we have first derivative, which is 5 exponential to 5t g of t plus exponential to 5t g prime of t, and then plus 25 exponential to 5t g of t equals 0. Okay, so let us do some cancellation. Let's see here. Negative 10 times this one is negative 50 exponential to 5t g of t. So here we have 25, we have another 25. So this one, and this one can be cancelled. And then we can just collect the other terms. So here we have actually 10 exponential to 5t g prime of t, and then plus exponential to 5t g double prime of t, and then here we have negative 50 exponential to 5t g prime of t equals 0. Okay, so actually this one and this one let this one and this one can be collected together. So we have and actually exponential to 5t is not equal to 0. So also we can just cancel exponential to 5t, exponential to 5t, exponential to 5t like this. Okay, so here we only have g double prime of t minus 4t g prime of t equals 0. Okay, so in this case, let us just integrate on both sides. So we have a g prime of t equals minus 4t g of t equals a constant c. Okay, so for this one, the solution will be something like exponential to. Did I make anything wrong? Oh, no. Oh, this one is not 50. This one is only minus 10. This one is minus 10. Okay, this one is minus 10. Okay, this one is minus 10. So yeah. Okay, so everything works correctly. So actually, this term and this one cancel each other. So finally, we have a g prime double prime of t to be 0. For g double prime of t is 0, g of t should be something like a plus bt. You take the first derivative, it becomes a constant. You take the second derivative, becomes 0. So it should be something like that. Okay, so here we should have x, the complementary solution, to be just say c1 exponential to 5t, and then plus we plug in this one into here, so we should have a plus bt exponential to 5t. Okay, like this. Okay, so here this one and this one are the same, so we have a plus c1 plus bt exponential to 5t. Okay, so this one is another constant, so we can just write it as a c1 plus c2t. exponential to 5t. So this shows you why this terms comes out. Okay. So this is for the second case, we come up with c1 plus c2t, and then for the third case, x double prime plus 4x prime plus 7x to be 0, and then the characteristic equation is s squared plus 4s plus 7 to be 0. And then the roots are complex. The roots are complex conjugate roots. So s1 is -2 plus square root of 3i, and then s2 is -2 minus square root of 3i. Okay, like this. Okay, so the real part is -2, the imaginary part is square root of 3. So here we have exponential to -2t, this is the real part. And then here we have a cosine, this is the imaginary part of the roots. Square root of 3t, square root of 3t, cosine and sine, and then c1, c2, like this. Okay, so if you just remember, then you can just write it out very quickly. You don't really need to derive it from time to time, you just need to remember, oh, this is for distinct real roots, you just plug in the real roots there, and then for repeated real roots, you just have the first order polynomial here, multiplied by this term is related to the roots, and then for complex conjugate roots, we have real part here and then imaginary part here. Okay. So the next step is to solve for the particular solution. For the particular solution, there are several types: polynomial, exponential, sinusoidal. Not for tangent, only sine and cosine. Even not for cotangent, cosecant, I don't remember. It's only sine and cosine. Yeah. Yeah, so for the fourth, fifth, and sixth, we multiply polynomial by exponential. We can still find the solution. Yeah, actually, this one is still very useful. And then also for, I think for this one, exponential function times sinusoidal function is very useful because actually, this one is actually exponential multiplied by the sinusoidal function. Exponential multiplied by the sinusoidal. So for the fifth one, you should know it very well. And then for polynomial, seldomly used. But some of the cases it will occur. But just for complete theory, we just summarize all of them here. And other than this equation, we may not guess this particular solution easily, but but this is quite enough. But if you really want to know how to solve for the others, maybe there is a solution, but you need to seek for some more complicated mathematics like the Fourier or Laplace transform to really solve for other solutions for the particular solution for the specific type of g of t. Okay, so here for the first type, if g of t is an nth order polynomial, we denote it as a p sub n to the t. So n stands for the order of the polynomial. Okay, so we can also assume xp of t to be another nth order polynomial. Okay, so let's see an example. So for we have x double prime minus 2x prime minus 3x equals 4t minus 5. So this is constant coefficient ODE, and on the right side this is a first order polynomial, 4t minus 5. Okay, with or without the zero order term, it is still first order. So even though without the minus 5, we should assume the particular solution to be a plus bt. But before going to there, we solve for the homogeneous solution first. So we just let the right hand side to be 0. So we have x double prime minus 2x prime minus 3x to be 0. And then for this equation, the solution is -1 and 3. So this is the homogeneous solution. And then we should assume the particular solution to be the first order polynomial with, because we have 4t minus 5 on the right side. And then we can plug in this one into equation 1. So we have a plus bt double prime minus 2 times a plus bt prime minus 3 times a plus bt equals 4t minus 5. Then we can just solve this one. So for this one, second derivative will be nothing but 0. And then for the first derivative, it will be b. So we have -2b here. And then here we have a -3a and then -3bt, like this. Okay, so equals 4t minus 5. Okay, so we can just collect the terms, -3bt, putting here. And then this one, we just put them in the brackets, and then equals 4t minus 5. So here we try to compare the coefficient. So -3bt and 4t. So here we have two first order polynomial equals each other, which means that all the coefficients should be equal to each other, which means that -3b should be 4. -3b should be 4, and then this term in the parenthesis should be equals to -5. And then here it is a joint equation with two unknowns, so we can solve it. And actually the solution will be a equals to 23/9 and then b to be -4/3. So here just plug it back to here. It is the particular solution. And then finally the complete solution to this equation is the complementary solution plus the particular solution. Here we don't have the initial condition yet, so we cannot determine C1 and C2 yet. If we have the initial condition, for example, x0 to be a value, and then x prime of 0 equals to another value, then we may be able to solve C1 and C2. But here, the initial condition are not given, so we cannot determine the unknown coefficient yet. Okay, so next is the exponential function. So if g of t is an exponential function, then we can assume xp of t to be an exponential function, like this one, exponential to alpha t. Then we can assume the exponential function, the particular solution to be a times exponential to alpha t. And then also we try to combine, this is the case 4. So if g of t is polynomial multiplied by exponential, like this, pn1 of t times exponential to alpha t, then we also assume the particular solution to be the polynomial with the same order n, and then multiplied by exponential to alpha t similarly. So for these two cases. Okay, so let's take a look at this example. So on the left side it is actually the same, on the right side it is polynomial of first order multiplied by the exponential function. So for the first step, we still solve for the homogeneous equation. So the homogeneous equation should be the same because the left hand side is actually the same as the previous one. And the next, we try to solve for the particular solution. So for the particular solution, this is a polynomial of first order multiplied by an exponential function. So we also assume the particular solution to be a first order polynomial multiplied by the exponential function with the same exponent. So we have a times exponential to 2t plus bt times exponential to 2t, like this. And then we can plug this one into equation 2 to solve for a and b. Okay, so here we have this one double prime minus 2 times this term prime minus 3 times this term equals this term. Okay, so here For the second derivative, it should be 4a exponential 2t. And then for this one, it is a bit more complicated. We have double prime of this term, double prime of the second term. So it turns out to be 4bt exponential to 2t. And then 2 times the first derivative of the t, and then the 2 times the first derivative of this one. So it will be 4b exponential to 2t. And then also for the second derivative of t will be 0, so we don't have the third term of this one. And then here we have a -2, -2, and then the first derivative like this, exponential to 2t. The first derivative will be 2 times exponential to 2t, so we have a 2a exponential to 2t. And then the first derivative of this one, we need to use the product rule. So we have a bt times 2 exponential to 2t, so this term. And then take the first derivative of this one, we have b times exponential to 2t like this. And then also this one here. Okay, so then we can just let me see whether we can do some cancellation or just collect the terms. So here we have 4bt exponential to 2t, and then we have minus 4b, and then we also have this one, minus 3b. So we have 4b minus 2 times 2 for minus 4b, and then minus 3 times this one will be minus 3. So these are the 3 terms. And then here 4a is this one, 4b is this one, minus 4a, and then minus 2b, and then minus 3a. So we collect all the terms, and then both sides should equal to each other so that the coefficient should match, which means that this parenthesis should be 6, and then this parenthesis should be 0. Okay, so we get this joint equation, and then we can solve for a and b, and we can plug it back to the particular solution here. And then finally, the complete solution will be the homogeneous solution plus the particular solution like this. Now, similarly, we don't have the initial condition, so we cannot determine the C1 and C2 yet. Okay, so the next case is the sinusoidal function, which is supposed to be the most useful one. Also for the polynomial of 0 order, polynomial of 0 order, 0th order is also very useful. Will also be very useful. And actually, for sinusoidal function or exponential times the sinusoidal function, which is still very useful. So if it is just a sinusoidal function, if it is sine of beta t or cosine of beta t or both, then we should assume the particular solution to be a times cosine of beta t times b sine of beta t, which means that if g of t has only the sine, you still need to assume the particular solution with both terms, cosine and sine. If it consists of only cosine of beta t, you still assume the particular solution with both terms. Okay, so yeah, so next, if g of t is exponential function times sinusoidal function like this, exponential function times this one, then you should assume the particular solution to be the exponential function times the cosine plus sine, the linear combination of cosine and sine. And then if it is a polynomial times exponential times sinusoidal, like this, polynomial times exponential times sinusoidal, then the particular solution should be polynomial times exponential times cosine and sine, and then with, yeah, which is very complicated. Actually, I seldom need to solve this with hand, but yeah, just for completeness of this theory. Okay, so let's take a look at this sample problem. Okay, so it says x double prime minus x prime plus x equals 2 sine of 3t. So first step is to solve for the homogeneous equation, and then yeah, just go to the homogeneous solution. And then on the right side, it is sine of 3t. So we just assume particular solution to be a times cosine of 3t plus b sine of 3t. And then we can just plug this one into equation 3. And then like this. And then we can just collect terms. This parenthesis multiplied by cosine of 3t plus this parenthesis multiplied by sine of 3t equals this one. So on the right side, we don't have cosine, so it's just like 0 times cosine of 3t. So here, this parenthesis equals to 0, and then this parenthesis equals to 2. So we have this joint equation, and then we can solve for a and b, and then we can just plug it back to here. So finally, the complete solution is the homogeneous solution here, and then plus the particular solution with a and b value, like this. Okay, so this is for the sinusoidal function. Okay, so up to here, you can solve at least 80% of the constant coefficient ODE. But there is a glitch here, is that just take a look at this example. If we have a equation like this, x double prime minus 5x prime plus 4x equals this one. Okay, so for the first step, you should solve for the homogeneous equation first. So you just pick the right side to be 0. Now we solve for it, so we can see the complementary solution to be c1 exponential to t plus c2 exponential to 4t, because the roots are just 1 and 4. So we have this term and this term. So here you can see this exponential to t and this exponential to t are actually the same. If you just assume the particular solution to be a times exponential to t, then you won't get the solution, because if you just plug it back here, then the left side should be 0. The left side should be 0 because this one is already the complementary solution. So this particular solution guess doesn't really work. So it's clear that we cannot find a for 4 as exponential to t is a solution of this one. So if you just plug in, left side will be 0, right side is this one, then you'll find no solution. So alternatively, we should multiply it by t. Something like the repeated real roots case. You can just, if you don't believe, you can just try to plug in xp of t to be just say h of t times exponential to t, and plug it back to equation 4, and then you will find h of t will be a first order polynomial, something similar to what I derived just now. Okay, so yeah, so we need to multiply by t, and then with this one, and then we plug it back to 4, we can actually find a. So here the solution will be the complementary solution plus the particular solution, but here the particular solution is not actually the exponential function, but we need to multiply by a polynomial. So here you can regard it as a 0 order multiplied by the exponential. Here we have a first order multiplied by this one. Okay. So if we have initial value problem, then we only need to just go through the order procedure. Just say for this one, if we have x, this is the second order constant coefficient ODE with this g of t, and then we have x of 0 and then x prime of 0. Then still for the first step, we should solve for the homogeneous equation, and this is the homogeneous solution. And then for the second case, this is a first order polynomial. So and then this is a sinusoidal. So the particular solution should include a first order polynomial and also the sinusoidal. But here we find that this one, this cosine or this sine of t is actually the same as this one. So we still need to multiply the particular solution by t here. So then we can just plug this one into equation 5 and then blah blah blah, just solve for a, b, c, d, and then we can find a, b, c, d to be this value. So the complete solution will be c1 cosine of t plus c2 cosine of t plus 4t minus 5t cosine of t. And then here we cannot stop yet because the initial condition given to you. So we need to solve c1 and c2 based on the initial condition or the initial values. So here, this is the solution. So we have x of 0 to be 5. So we can just plug in 0, 0, 0, 0, 0, 0 to be 5, And then we can solve c1 to be 5. And then this is the solution. And then we can take the first derivative to be like this. And then we can just plug in 0 here. So that we have an x prime of 0 to be 0, 0, 0, 0, 0, 0. And then we can just solve for c2 to be 2. So now with the initial value or the initial condition, we know the solution to 5 will be this one, Okay, so I think, so that's all for today, and